Okay, so everything that you're going to do today, you need to be able to do without a calculator. So go ahead and put it away so that you're not even tempted. So we're going to talk about log functions. These should ring a bell because I know you talked about them in Math 3, and if you had AFM, you've had a little bit more experience with them. Um, I'm going to teach this very slowly, um, like you've had very little experience with them, okay? So the basics of a log is that it has two different levels. It has the log, then this is what you're logging. So this is log of x. This is not log times x. So that's log of x, and then this little guy down here is your base. So the way that you would read all this mess that's highlighted is you would say log base A of x. Log base A of x equals y. Okay, now log form and exponential form are inverses of each other. So they're cousins. Exponential form, which we've already dealt with, a to the y equals x. Okay, so let's write something that's a true statement. Let's say 5 squared is 25. Okay, and that is exponential form because I see an exponent. Okay, to turn that exponential form into log form, what is being raised to the power becomes the base of your log. What it equals becomes the of. And the power is the answer. So what logs do is it finds the power. Okay, now those of you who've had AFM hopefully remember snailing it. All right, and here's what that means. This is why we call it snailing it. It is, let me erase all of this. It is to take something from exponential form and put it into log form. It is log base A of x equals y. And we think that looks like a snail. So snail it. Log base A of x equals y. So log base 5 of 25 equals 2. All right, look at this one. This is 2 cubed equals 8. So log base 2 of 8, log base 2 of 8, equals 3. So you're sort of going in this almost circle, and we call it snail. So what I want us to do for these examples is we're going to snail it. So we're going to take this log form, which is obviously in log form because I see the word log, and I'm going to snail it and put it in exponential form, and I'm going to see if I can figure out the power that will make that happen. So what these are all missing is this equals y part. And you can set it equal to y, you can set it equal to x, you can set it equal to a smiley face, I don't care. Or you can just know, you know what, there's a variable over here. So you can let it be, like I said, x, y, q, I don't care. So if I snail this, this is going to be 2 to the x equals 32. So now I just need to figure out what power can I raise a 2 to get to 32. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. 1, 2, 3, 4, 5. 2 to the 5th. 2 to the 5th equals 32. Now, I know you're watching this on a video, and I know you very well could have your calculator out. I know that you know there's a log button on your calculator, and some of you even know how to do the change of base. But believe me when I tell you that you need to be able to do these without a calculator. So this is how you need to learn it. This is how you need to practice it. because this is how you're going to be assessed on it. Okay? So don't cheat yourself. No calculators. Okay, number 2. 3 to the something equals 27. So 3 to the x equals 27. So I'm not doing 3 times what? So like x does not equal 9. I'm trying to raise 3 to a power to get to 27. Well, 3 times 3 is 9. 9 times 3 is 27. So that would be 3 cubed. So the power needs to be a 3. Okay, those are the only 2 straightforward ones we're going to have. Okay. This is where watching those videos before school started is really going to pay off. And if you struggle with this, then I highly recommend you go back and watch the power videos, the exponent videos. Okay, I'm going to set this equal to x. So 4 to the something equals 2. Okay, now this is different because I'm taking a 4. I'm raising it to a power and I want it to get smaller. Okay, well remember, when you have a power, it could be a whole number or it could be a fraction. And if it's a fraction, remember you can write roots as powers. So like if I had the square root of 25, I could write that as 25 to the 1/2. Power's a 1, root's a 2. If I had the cube root of 6, I could write that as 6 to the 1/3. That just means I want to cube root it, okay? So powers that are fractions are roots. So power over root. Now, I know that because the number is getting smaller, I know it needs to be some sort of root. I also know that the square root of 4 is 2. So I want to square root it. So I want my power to be a 1/2. I'm not halving it. That's not what I'm doing. That's not how I'm going from a 4 to a 2. This is 4 to the 1/2, which means the square root of 4, which is a 2. That's why my power is a 1/2. Okay, let's look at number 4. 36 to the something equals 6. Well, I know the square root of 36 is 6. So my power needs to be a 1/2 because that's what's going to make me square root the 36. 8 to the x equals 2. Okay, well the square root of 8 is not going to get me a 2, but I know the cubed root of 8 because I know 8's a cube. So the cube root of 8 is 2. So I know that power needs to tell me to cube root it. So my power is going to be a 1/3. Remember, power over root. I want my power to be a 1 because I don't want it to get any bigger, but I do want to cube root it. So that's why it's a 1/3. Okay, number 6. 144 to the something equals 12. Well, I know the square root of 144 is 12, so x needs to be a 1/2 because that would make me square root it. Okay, 64 to the something equals 4. And again, I'm staling it every time. I'm setting it equal to x and I'm staling it. Now, the square root of 64 gets me to an 8. That's not what I want. I need to get to a 4. Well, 4 cubed is 64. So the cubed root of 64 gives me 4. So I know that x needs to be a 1/3. 16. 16 to the something's got to get me a 2. Square root of 16 is not going to cut it. That only gets me down to a 4. Cube root 16 is not a cube. But the fourth root, 2 times 2 times 2 times 2, 4, 8, 16. Yep. So I need to fourth root it. So x needs to be a 1/4. And I'm assuming that you guys are pausing as you need to so that you can process and digest or rewind it so you can hear something. You go through this video as needed. as slow or as fast as you need. Okay, changing gears. So 10 to the x equals 1 over 100. Okay, now I want you to ignore the fact that there's a fraction, okay? I want you to get me from a 10 to 100. Well, that would square it, okay? So I know my power needs to be a 2 because 10 squared gets me 100. The kicker is it moves to the bottom. And there's something you can do with exponents that make it move, and those are negative exponents. So that 2 needs to be negative. All right, now look at what you just wrote. 10 to the negative 2. This says square me, move me. Square me, I'm 100. Move me, I'm a 1 over 100. So negative exponents move it. So I don't want you to look at, oh, I've got to go from a 10 to a 1 over 100. I don't want you to look at that. I want you to get me from a 10 to 100. That would be squaring it. And that it needs to move. So that's why it's a negative. Okay. So number 10. 3 to the x equals 1 over 27. Okay, ignore the fact that that's a 1 over 27. Get me from a 3 to a 27. And that would be cubing it. Now it's not a plain 27, it's a 27 on the bottom, so the power needs to be negative. So this is 3 to the negative third, which means cube it and move it, and that's why it's a 1 over 27. Negative exponents do not make numbers negative. They just move them. Okay. 5 to the x equals 1 over 25. Okay, to get me from a 5 to a 25, you need to square it, and it's 1 over, so you need to move it. 2 to the x equals 1 over 32. Okay, get me from a 2 to a 32. I think we figured out early that was a fifth power, and it moves to the bottom, so negative 5. Okay, 5 to the x equals 1 over 125. Well, let's see. 5 squared is 25. 5 cubed is 125, and it needs to move. Okay, now putting two concepts together here. 49 to the something equals 1/7. And again, I'm still just snailing it. I'm just not writing it out every time. So 49 to the x equals 1 over 7. Okay, ignore the fact that it's a 1 over 7. Just get me from a 49 to a 7. Well, the square root of 49 is 7. So that means 49 needs to be to the 1/2 power. That'll get me to a 7. So I know my power needs to be a 1/2. However, the answer is not a 7, it's a 1/7. So there's movage. So it needs to be negative. So the 1/2 does the square root. The negative moves it. So just know what all the pieces do. Okay, here's another one. 16 to the something equals 1/2. Okay, just get me from a 16 to a 2. Well, it's got to go smaller, so it's got to be a root. Square root of 16 is 4. That doesn't work. Cube root of 16 doesn't exist. Fourth root of 16 is a 2. So I need to fourth root it. So my power needs to be a 1/4. That's the root part. But that will just get me a 2. Now I need a 2 that ends up on the bottom, so it needs to be moved. So that's why it's negative. Again, know what all the pieces do. Okay. 1/8 to the x equals 2. Okay, ignore the fact that one's a fraction and one's not. Just get me from an 8 to a 2. Well, I would have to cube root the 8 to become a 2. So my power would need to be a 1/3. That gets me to a 2. Now, This 8 starts on the bottom, but the 2 ends up on the top. So there is moving going on here. So it needs to be negative. So the 1/3 cube roots it and goes from an 8 to a 2. The negative takes the 8 from the bottom and moves it to the top. Okay, sidebar. What if I had this? All right, ignore the fraction-y part. Just look, I need to go from an 8 to a 2. Well, that's cube root. So my power is a 1/3. Did anything move? No, it all stayed on the bottom. No negatives needed. Nothing moved. I started out on the denominator. I ended up in the denominator. Nothing moved. If I went from an 8 to a 1/2, I would need to cube root it and move it. If I go from a 1/8 to a 2, I need to cube root it and move it. That's why both of those exponents are negative. This exponent is not negative because nothing moved. But in all three cases, I needed to cube root it, and that's why it's a 1/3. That's a great set of examples right there. Okay. 25 to the something equals 1/5. Okay. To get me from a 25 to a 5, I need to square root it. 25 starts on top, ends up on the bottom, needs to be negative. Okay. These last three are good. Okay, I need to go from a 4 to an 8. It's getting bigger, so it's going to be a power. Well, the smallest power is a 2, and 4 squared is a 16. It's too big. I've overshot it. So what if I rooted it first and then powered it up? Well, the only root I can do of a 4 is a square root. So I'm going to put a 2 on the bottom. Okay, so all that does is square root the 4, and that gets me a 2. Now get me from a 2 to an 8. Well, I would need to cube it. So I'm going to cube it. Remember, this is power over root because that x represents your exponent. So if I had 4 to the 3/2, that means the square root of 4 cubed. The square root of 4 is 2, and 2 cubed is 8. That's where I start. That's where I end. So there's my answer. Okay, let's try this one. 9 to the x equals 27. Well, 9 squared is 81. I've already overshot it. But I can square root of 9. That gets me down to a 3. Then to take a 3 to turn it into a 27, I need to cube it. Again, power over root. Root it to get it smaller, then power it to build it up to where you need to go. 8 to the x equals 16. 8 squared is 64. So the smallest power I got has overshot it. Now I can't square root an 8, but I can cube root an 8. So cube root an 8, that gets me down to a 2. 2, 4, 8 to the 4th. Gets me up to a 16. So this is what I did. 8 to the 4/3. So that's the cube root of 8 to the 4th. The cube root of 8 is 2, and 2 to the 4th, 4, 8, 16 is a 16. Okay, there are some properties that you need to know. Log base 3 of 1, log base 6 of 1, log base I don't care of 1 always equals the same number. Let's figure out what it is. Okay, snail this. So this would be 3 to the x equals 1. Well, what power can it raise a 3 to and get a 1? Please don't say 1/3. I'm not multiplying 3 times 1/3. If you say 3 to the 1/3, that's the cube root of 3, and that's not a 1. What's a power that you can raise something to that'll make it a 1? That's a 0. anything to the 0 power is a 1. Again, videos from before the school year started, those power videos. Second one, 6 to the something equals 1. Well, anything to the 0 power is a 1. So log base A to the x equals 1, x is going to equal 0. Log base A of 1 is going to equal 0. Always. It will always equal 0. So log base, I don't care, of 1 will always equal 0 because I want my result to be a 1. I don't care what your base is, my power needs to be a 0 because anything to the 0 power is a 1. So this 1 is saying, hey, I want my result to be a 1. This being a 0 says, okay, I got you. Your power needs to be a 0. So log base whatever of 1 is always a 0. And that's one you just need to know. Okay, and then check out number 2, log base 4 of 4, log base 6 of 6, log base A of A. Okay, well, let's snail this. If I set that equal to x and snail it, 4 to the x equals 4. What's your power need to be? It needs to be a 1. I need to raise it to the first power. 6 to the x equals 6, x needs to equal 1. A to the x equals a, x needs to be equal 1. So it is always equal to 1. So log base something of the same something is always a 1, as long as those are the same. So log base 5 of 5 is a 1. Log base a star of a star, it's a 1. As long as the base and the of are the same, it is always a 1. Okay, last thing we need to do is we need to graph. Now, when we started this, I explained that exponential and log functions are inverses of each other. Okay, well, we've talked about inverses before. We've talked about inverses reflecting on the line y equals x. You know from the last lesson that an exponential's home base is 0, 1. It has an asymptote that runs below it, and this one is growth. So if I take that in the mirror, this point that's 0, 1 becomes 1, 0. So a log's home is at 1, 0. An exponential's home is at 0, 1. Now, look at the purple dotted line, that purple asymptote. That's the asymptote for an exponential function. The asymptote for a log function is vertical. And it is always one to the left of that blue dot. But we're going to shift that blue dot. And then the log graph looks like that. This is the asymptote that it's pulled towards. Remember, this is not an asymptote. This is the reflection line. So he's pulled towards, and then he hits that point, and then he shoots away. Okay, so let's talk about growth and decay and flipping and shifting and all that stuff. Okay. So for the first one, this is going to be growth. I'll explain when it becomes decay, but for right now, it's growth. We talked about the home point being 1, 0, and the asymptote being 1 to the left. It is towards the asymptote, hits that point, and then shoots away. And you always, always, always label that point. Number 2 is also growth. And now I have a -1 inside my function. Well, you know from Unit 1 that if it's a shift inside the function, it's right, left, opposite the sign. So I know that this sucker is going right 1. So this was home, but it is now being shifted right 1. The asymptote also shifts. The asymptote is always 1 to the left of your main point. So the asymptote is now there. Close to the asymptote, hits the point, shoots away, label my point, 2, 0. That's how I know you got your shift right. Okay, plus 2 outside the function is up, down, true to the sign. Again, this guy's growth. I'll show you what he looks like when he's decay. And this is going to go up 2. So again, home base is right here at 1, 0, and I'm going to shift that sucker up 2. Now shifting up or down does not move your asymptote. The asymptote again is 1 to the left. I'm going to erase that point. So I'm tied to the asymptote and then pull away. And that point is 1, 2. Okay. All right. Now, I want you to look at 4, 5, and 6. Number 4, I see a negative on the x inside the parentheses. He has a negative on x inside the parentheses, and he has a negative outside the log. Okay? When you have a negative inside, that is going to be a flip over the asymptote. So that's going to be a flip over the asymptote. That's going to be a flip over the asymptote. Now, what a negative does on the outside, there's your decay. There's your decay. Okay. So because this is a positive in the front, we are growth. Same thing for number 5, positive in the front, so we are growth. All right, we are going to flip over the asymptote. Okay, I also have a shift. Now you guys remember from unit 1, I said when the inside is funky, set it equal to 0 and solve it and go true to the sign. So 2 minus x equals 0. I'm going to add x to both sides. I'm getting a positive 2. So I'm going right 2. So I'm going to my natural starting point. I'm going to go right 2. So that's where I land. Asymptote is 1 behind it. Going to erase that guy. All right, so here I sit. I'm growth, but I am flipped. Now, I am not a good, let's see, I can't flip something that I don't see all the time. I can flip a parabola, that's not a problem. Like I can flip the basic functions. I can't flip logs without seeing what the original graph looked like. That's just me. That's a hang up for me. So what you're going to see me do when there's a flip is I'm always going to draw the original, but I'm going to draw it in a dotted line because now I can flip it because I can mirror it. But I have a really hard time drawing that blue solid line without that blue dotted line. If you can do it, fantastic, knock yourself out. I cannot. I'm living within myself. I understand my limitations, and that is one of them. I need to label this point. So the vertical dotted line is the asymptote. That has to be there. But the curved dotted line is just for me. It's totally fine to leave it there. You do not have to erase it. It's a dotted line, so I'm not drawing it as a solid line. Okay, number 5 is growth because it's a positive in the front. I am going to flip over the asymptote, and I'm going to go down 3. So I go to my starting point, and I'm going to shift down 3. 1, 2, 3. Plop a dot. Okay, then I'm going to come back here and erase that dot so I don't get confused. Asymptote is one behind it to the left, and I am growth. I am growth, but I'm getting flipped. So I'm going to ride along the asymptote, hit the point, and peel off. But again, that's a dotted line because that's not my actual graph, because now I have to flip it. So if I flip it over the asymptote and then draw, and then that point is -1, -3. Okay. Number 6. All right, we are now decay for the first time. We have no flips. We are left 1 and up 1. So I'm starting here. I'm going left 1, up 1. So this is where I end up. I'm going to erase both of those points so I don't get confused. Asymptote is always 1 to the left. And no flipping and decay. Okay, so now decay starts high near the asymptote, comes down, hits that point, and peels off. There's your decay. And his point is 0, 1. Okay, so again, it's a video, so pause, rewind, do what you need to do so that it soaks in. Okay, then the last thing we need to talk about are natural logs. Natural logs are base E. All right, now you have a symbol that represents a number, and that's pi. And everybody knows that's 3.14, and some people know many, many more decimals than that. E is also one of these numbers. You have an E button on your calculator. We're not really going there today. But E is a number. It's 2.6 something or 7 something. I can't remember. But it's 2 and some change. It's just over 2.5. So E is a number. Okay. E is natural log is the inverse of e to the x. Okay. So natural log is written like this. Now I don't recommend that you do that because I don't want you to think that's a 1. So every time I write ln, I use a cursive L. So ln of x. Now ln of x is the exact same thing as log base e of x. But they don't, in the math world, you don't ever write log base e of x. If it is a base e, you're going to write ln of x. Now notice there's no base. Well, there's no base written, but it is understood that that base is e. So when I write ln of 5, I know that that's log base e of 5. I just don't write it. His base is always an e, and when his base is e, it becomes an ln. You'll never have an ln whose base is anything other than an e. Okay? ln stands for natural log. Okay, so ln of 1, well, we've talked about this. Any log of 1 equals 0. Here's why. If I set this equal to x, now remember his base is e. If I snail it, I get e to the x equals 1. And e to the 0 is going to give me 1. Okay, ln of e. Okay, if I set him equal to x, remember his base is an e. So e to the x equals e if I snail it. So x has to equal 1 for that to happen. Also, do you remember way back when, 20 minutes ago, we said log base 5 of 5 was a 1. Well, guys, this is the same thing as that. This is log base e of e. That's a 1. So ln of e is 1. ln of e squared, okay, let's snail it. So this is e to the x, I'm snailing it, equals e squared. So what does x need to be? Well, x needs to be a 2. ln of e to the 8, going to be an 8. ln of e to the, that's a star, is star. the point is, if you have ln of e to the 1,286, it's 1,286. So ln of 1 is always 0, and ln of e is always 1. Ln of e to a power is always that power. Okay? And then the graphs are exactly the same. They are still logs. It follows the exact same pattern. This is a log. It's going to start at 1, 0. This is shifted right 2. He is growth. Remember, what makes him decay is the negative in the front. There's your decay. So growth, and I'm going right 2, 1, 2. So there he is. There's the asymptote and growth. And that point is 1, 2, 3, 3, 0. Always, always, always label your point. Okay, this has a negative on the x, so there's your flip. 2 minus x is weird, so I'm going to solve it and go true to the sign. So here I am, right 2. Asymptote is 1 behind it, to the left. I'm growth. I didn't write that part. But I'm flipped. So again, I have to draw it so I can flip it. And that is at 1, 0. So he was shifted right 2, but because of the flip, he ended back up where he started. However, he's flipped over. Asymptote has to be there. The dotted curve line does not have to be there. This one's decay, and he's going up 3, so I'm going to my starting point. 1, 2, 3. Asymptote didn't move because I didn't go right or left. Decay, start tall along the asymptote, hit the point, and shoot out. 1, 3. There you go. The whole first half of your test is graphing exponentials and graphing logs with no calculator. So make sure you know shifts and flips and growth and decay.